Hello everyone, and welcome to the PLDI machine learning session. We're going to have 6 very interesting papers. We're going to start with Ziyang Li on his paper.
Hello everyone, welcome, and I hope you are having a great day so far. This is Ziyang Li, and I'm from the University of Pennsylvania. Today I'm going to present to you guys about our work, Scallop, a neurosymbolic programming language. This work is done with my colleague Jiani and our advisor, Professor Mayur. To start, let's talk about 2 prevalent paradigms of modern programming. Traditionally, there are classical algorithms and learning-based algorithms. And for classical algorithms, they are usually suited for some exactly defined tasks. Such algorithms also usually work on highly structured inputs. Some examples include sorting algorithms, finding shortest path on graphs, or solving Boolean constraints, and so on. On the other hand, we have deep learning models. They're often employed for tasks that are data-driven, cannot be hand-programmed, or have unstructured input. Examples include detecting objects in an image, semantically parsing natural language text, or control with signals from physical environments. There used to be a huge gap lying between these 2 paradigms of programming. And Neurosymbolic is here to combine the both worlds. For classical algorithms, we name it as symbolic, and for deep learning, we use the word neural. Combining them together, we have neurosymbolic. Specifically, neurosymbolic frameworks should offer a tight integration between classical algorithms and deep learning models. It should also allow to incorporate domain-specific knowledge in principled and systematic manner. It should also provide more interpretability and trustworthiness over black box neural networks. Last but not least, it should generalize better to unseen inputs with better data efficiency. There is a landscape of neurosymbolic methods. We roughly categorize them along 2 axes. The first axis, the horizontal one, is practicality, and the vertical one is generality. Inefficient and specialized methods, as we see in the bottom left corner, they're certainly uninteresting. But on the bottom right corner, there are a set of specialized neurosymbolic methods designed for particular tasks. They are quite efficient and effective, but they cannot generalize to other examples. In the pursuit of a general and expressive neurosymbolic programming framework, there have been people working on languages that are very general, but somewhat inefficient, or somewhat practical, but limiting on their expressiveness. Therefore, we set out to develop a new neurosymbolic programming language that is both general, expressive, practical, and configurable. And we place Scallop right there. We introduced Scallop as a declarative language based on Datalog. It supports reasoning patterns such as recursion, stratified negation, aggregation, and has language features such as type inference, foreign functions, foreign predicates, and so on. Any program written in Scallop is differentiable and will be empowered by customizable and scalable probabilistic reasoning backends, aka provenance, which we will talk about later in this talk. Scallop provides a comprehensive and open source toolchain for debugging and integration with the PyTorch framework and many other machine learning frameworks in the future. And the goal here really is to provide a unified language and framework for programmers to write neurosymbolic applications with ease. Now with that in mind, let's see what Scallop can really do by looking at a motivating example, that is Pac-Man maze. Here, inside of this game, we want to train an agent to look at the environment and control the Pac-Man to reach the goal, that is the flag in blue, while avoiding all those enemies which look like ghosts. More specifically, the game is settled on a 5x5 grid. At each time, the agent can take simple actions such as up, right, down, and left, and for each game session, the environment is completely randomized, meaning that the initial position of the Pac-Man and the flag can all change. Also, the only feedback that the agent can receive will be, after some sequence of actions, have we won or not? If we have won the game, we have a reward of +1, otherwise we have a -1. The challenge of this game is really that a perfect agent needs 2 complementary capabilities. The first one being that we need to correctly perceive the environment from the image only, and then we also need to plan the path logically and systematically. Notice that we don't have a separate data set telling the perception model what each type of entity is. It doesn't really know even about itself, the Pac-Man that is controlling. The only feedback that the model can receive is the reward given at the end of each game. In this case, Neurosymbolic is really here to the rescue. We can decompose the task into two separate parts, namely perception and reasoning. For perception, we ask a neural network to recognize the entities shown on the image. We might employ a traditional computer vision model. For example, say a convolutional neural network, CNN, as denoted by m theta right here. To parse the image, we call this model the entity extractor. On the other hand, for reasoning, we want to take the perceived entity positions and plan for the optimal action to take. For this, we are going to use Scallop to write a program that can compute a score associated with each action. Conceptually, we can think about the scores encoding the probability of our agent eventually reaching the goal if we take that action. Let us take a look at the actual Scallop program as the path planner. The Scallop program, the Scallop language is declarative and concise. While there are some lines that we haven't shown for brevity, the whole program can be written in just 11 lines of code. On the top, we define the enum type of action, like up, right, down, and left, and we also define a bunch of relations, action, goal, actor, goal, and enemy, which we treat as input relations. Notice that these relations contain extracted entity position from the neural network. They are really forming probability distributions rather than discrete values. Inside of the program, we have used features such as recursion for finding the optimal path and also negation to avoid the enemy. At the end of a program, we compute the relation named next action, which checks if taking such action can give us a safe path towards the goal. The benefit of using our Scallop solution is astounding. While DQN is known as Deep Q Network, which is a traditional reinforcement learning model, takes more than 50K training episodes to reach only 85% of success rate, our solution just needs 50 episodes to attain an almost perfect success rate of 99.4. Here we achieve all of the benefits of the neurosymbolic paradigm, such as data efficiency, accuracy, and interpretability. Let us see a demo. This is a real-time screen recording starting from training the agent. You can see that on each grid cell, we render a small marker showing that what the neural network thinks the cell contains. You can see that initially, the network has no idea what the entities are, not even the Pac-Man itself. But gradually over time, it learns that the yellow Pac-Man is the actor that we're controlling, and the enemies are becoming red as well. If you look at the flag, you see that it's not so green as you would expect, but that is normal because we haven't hit the flag so far. If we hit the flag for enough amount of times, then it will start to learn that the flag is the goal that we need to reach. If we jump to the testing, right after 50 episodes, we see that our agent just rushes through all of the environments. You might not see it clearly, but this is actually 100% success rate so far. We have demonstrated Scallop's use inside of a typical reinforcement learning environment, but we note that Scallop is far more than that. It is robust and supports many different learning paradigms, including supervised learning, training with weak supervision, semantic loss, integrity constraints, fine-tuning, and even integration with large language models such as GPT. Now, with that motivation in mind, how does Scallop work exactly? Scallop programs written by users are compiled. It goes through multiple stages of internal representations, which we call front IR, back IR, and subsequently Scallop RAM, where RAM stands for relational algebra machine. For those of you who are familiar, relational algebra is a term in database community, and this also makes Scallop a relational database query language. In order to define the formal semantics of Scallop, we define it on SCR-RAM, which is actually conditioned on a selective provenance under Scallop's extensible and customizable provenance framework. In short, a provenance structure is an algebraic structure that specifies some tag that can be associated with the execution. In particular, we have the tag space T and defining the domain of some extra bit of information associated with the data being processed by Scallop. This makes Scallop very different from traditional Datalog systems where they're typically using on-text semantics. And in our case, we are using tag semantics where for each tuple, each tuple is associated with some extra bit of information, let's say T1, T2, and T3 right here. And when the information flows, we might get new tags that are compositions of existing tags. Putting into some context of actual probabilistic reasoning or heuristics for probabilistic reasoning, we can compute probabilities that are associated with tags. And these give a lot of freedom in customizing the underlying semantics of Scallop, where we can have provenance for discrete probabilistic and differentiable reasoning capabilities. That is indeed what we have in Scallop. There's a built-in library of more than 20 provenance structures, and that ranges from heuristic provenance for approximating probabilities to exact ones for probabilistic reasoning. In short, with the provenance framework, the syntax of Scallop program remains very familiar to programmers, but we also allow to customize the underlying semantics and subsequently the granularity of probabilistic reasoning, learning performance, and scalabilities. For the final part of this talk, let's see how good Scallop really is. We have compiled a benchmark suite of 8 machine learning tasks spanning the domain of computer vision, which requires the understanding of images and videos, to natural language processing, and even ones requiring multi-model capability. This means that Scallop's probabilistic relational database schema becomes the common interface for different models for different modalities to interact with each other. That include text, images, videos, knowledge graphs, programmatic queries, and so on. Our overall performance showed that Scallop can attain comparable, if not superior, performance even against neurosymbolic methods specifically designed for some tasks, such as HWF, clutter-G, and so on. It is worth noting that on the task of clutter, our method significantly outperformed fine-tuned large language model GPT-3 by 20%. Lastly, we want to discuss some additional benefits of using Scallop besides attaining accuracies. On the handwritten formula task, our Scallop solution attains comparable performance to the state-of-the-art neurosymbolic method NGS, which is specifically designed for the task. Even when trained with only 50 or 25% of the data, our solution still has more than 90% accuracy. For generalizability, we have already demonstrated the Pac-Man maze one, and on the clutter dataset, our solution degrades less severe when the input problem becomes harder. If we look at the performance of GPT-3, we see that it suffers from a huge drop in performance when encountering harder problems. And lastly, we have Scallop providing interpretability. Since our solutions help learn the intermediate labels for the Mugen task, this is a fine-grained video semantics, and for the Pac-Man, we have learning the representation of the arena. This makes our solution way more transparent than fully end-to-end neural models. In conclusion, we have introduced Scallop, which is a new neurosymbolic programming language. We have our website, scallopland.github.io, which hosts documentation, downloads, resources, and past tutorials, including the one we just did for this PLDI. We thank you for your attention, and I'm happy to answer any questions.
Okay, thanks for the great talk. I'm just wondering, in your Pac-Man example, I'm just wondering what your framework is learning. So does your framework also learn this pathfinding strategy or just learning image recognition?
Right. For the Pac-Man example, we are not learning the pathfinding strategy. That strategy is specified by a hand-coded Scallop program.
Okay. So in all of other examples, or is this always? I mean, is the rule always fixed, or does your framework learn these kind of rules?
There are a couple of examples, specifically clutter, where we actually learn the underlying rules, but under a specific template. And for the other ones, we are assuming there is a very general structure, for example, like solving for linear temporal logic or something like that to specify the logical components. And there's always like a logical components up there. Yeah.
Okay, thank you.
Hello. I have a question about your claims regarding interpretability. How do you quantify this? The reason I ask is because in my experience, if you synthesize 20,000 lines of prologue or datalog with recursion and negation, it tends to be very messy as well. And partly this may be a problem that I don't have a good way of quantifying this. How do you approach that problem?
Right. I want to make a clarification that not a lot of Datalog is synthesized right here, so we're not producing like tens of thousands of lines of Datalog code. And mainly the interpretability is on on the learning side, where when we are comparing with black box neural networks. Let's say we're doing a task of comparing videos with text. A typical neural network would like just take their embeddings and then see if they're similar to each other. But like in our case, we actually learned the video semantics that is underlying each of the video. So that is providing more transparency over the pure black box embedding that we're seeing from neural networks.
Thanks very much.
Yeah, thanks.
I guess I was wondering whether, in your experience, you've noticed cases where the Scallop program does not converge. And in that case, what sort of feedback does the user get, or what sort of strategies do you employ?
Right. So yeah, there are actually some examples that we have encountered this. In those cases, what I would usually do is that we start a debugging session, because Scallop can be used in different scenarios, not just directly connected with neural networks. We start with some simple examples and see if just hand code those probabilities and databases and see if the computation process goes smoothly. And then after that, we start to integrate that with neural networks. So in that case, we have more knowledge about how good our model is in predicting those probabilities. And then after connecting with neural networks, what we usually tend to do is we also look at because we have provided more interpretability, right? Like we are learning a lot of intermediate labels. And then what we can debug is that we look at the intermediate label and then see how well they are doing. And then if there are intermediate labels that are not learning correctly, then we say either it's the number of supervision not being sufficient, or our program is just not enough to provide the supervision to the model. And in that case, there are actually a lot of ways that we can add on to the program that we are writing. We can write semantic loss, integrity constraints, in order for more supervision to be provided into training the underlying neural networks. So yeah.
Yeah, thank you.
All right, let's take the speaker again.